So where do you guys stand with functors? Should we move on to natural transformations or? Yeah. Okay. Okay. We'll do it. Oh, actually, let me do one last thing. So let's take this little category. So in category theory, every category is important. Even this thing. So this is a category that has two objects. It has identity morphisms I don't draw, and it has two morphisms from A to B. Actually, I'll call this A, and I'll call this V, and I'll call this S and this T. And I'm thinking of these words. The way I picked the letters was arrows, vertices, source, and target. But this is a category. It's got two objects, and it's got four arrows, and you can only see two of them because two are identities. And a functor from this to set, what is that? So I'm going to call it G. So I'm going to need G of A, and it's a set. And G of V is a set. And I'm going to think of G as a graph, and G of A as the set of arrows in G, and G of V as the set of vertices in G. So G is a graph, but I'm thinking of it as a functor. Which way am I thinking of it? I don't know. I'm thinking of it both ways, and I'm translating between them because the set of functors from this to this is exactly the set of directed multigraphs, which I usually call graphs. So what do you do? Good question. And I need I'll get to that, and two functions. So now every morphism in here needs to go to a morphism in set, meaning a function. So functions, G's version of S and G's version of T. I'm not going to do that. G's version of S, taking G of A. Every arrow in G gets a vertex. And G's version of T, target, takes every arrow in G and gives a vertex. And you could write all this data down in two tables. You could say G has a version of V. And I'm going to make an identifier, a unique identifier for each vertex, or arrow, sorry. So I have arrow A, B, C, D, E. And here's my table. And I'm going to have an S, G of S, and G of T. G of S is supposed to be a function from G of A to G of V, and I haven't drawn G of V yet. So I might seem like I'm very out of order, but I'm trying to just get all this stuff written while still talking the whole entire time. So ID, 1, 2, 3, 4. And A is G of S column. I'm going to write down this function that takes a G of A and returns a G of V. So G of S takes A and gives 1, takes B and gives 1, takes C and gives 2, 2, 1. And G of T goes to, say, 3 and 4. Let me change this to 3. And 1 and 1 and 2.
How does T and S and A relate there?
So S is a map from A to V, and T is a map from A to V in this very weird category that doesn't seem to have any, people ask, what's inside of an object? There's nothing inside of an object. It's just an object. I can't see in it. But I have this category over here with two objects and two morphisms plus the identities. I have this category over here which is all sets and functions between them. And I'm saying, what does it mean to be a functor? It means I assign a set for this one and a set for this one. I assign an object and set for each object here. And I assign a morphism and set, meaning a function, for every morphism here. That's this one and this one. And the identities I'm not going to write because they're just identity functions.
Why are you calling A arrow and B vertex?
Right. Good question. So far I've given you the data of a functor. Because I've given you a set, G of A. So G of A is going to be the set 1, A, B, C, D, E. G of V is going to be the set 1, 2, 3, 4. And G of S and G of T are functions that take anything in G of A and gives back something in G of V. So I've put all that sets and functions into table form. And why is this called an arrow and graph and all that stuff is that I'll take all my vertices and put little dots under them. And I'll take all my arrows, all my G of A's, and A is going to be an arrow whose source, G thinks the source of A is 1, and the target of A is 3. It thinks the source of B is 1, and the target is 4. It thinks the source of that one is C is this, and D is this. And that's what multigraph means. You can have 2. And E is 3 to 2. So there's G pictorially. But if I drew any graph in the world, I'd take all my vertices and put them in this table. I'd take all my arrows and put them as the ID column in this table. I'd put my source and my target function, and I'd get back a bunch of tables full of the data for my graph. So this is the database you need for a graph, but it's also the functor from this little category to set. So in the book I wrote, this is this perspective that's kind of throughout. Is like you can think of functors to set as databases. You just take every dot here and make a table. You take every arrow coming out of a dot and make it a column. And you get a database. And tons of stuff from category theory carries over from that into database world from that kind of translation system. So what I'm saying is that there's a category of, that there's something called a directed multigraph, but I just call it a graph. And a graph is the same thing as a functor from this little category to set. So you might call this the graph indexing category. But in the book, I call it this database schema for graphs. It's the database schema for graphs. It tells you what the tables are and what the columns are. And if you fill that database with data, you get a graph. So now I want to talk about natural transformations. Oh, I didn't start my clock again. Okay, so. But I think I'm going to be behind, and I might not do that thing where I let you choose. At the end, I might just go slower than expected, and I think that'll work out. So what is a natural transformation? So at this point, when I talk about natural transformation, a lot of people feel like this is too much. Like it's like, okay, I hit my level. I don't know if that's going to happen to you. Okay. So suppose you have categories C and D. Someone wrote a book called The Joy of Cats, and it's about categories. Let C and B be categories, and you suppose you have F. If I write F comma G taking C to D, that just means I got two terms, two functors. It's not a pair. Well, it is a pair. The pair of functors, C to D. B functors. So this is the setup where you talk about whether you have a natural transformation. So if you have two functors from Hask to Hask, say list and tree, if tree is one, or list and anything. You have two functors from Hask to Hask. You can ask whether there's a natural transformation between them or not. Or maybe you have lots of natural transformation between F and G. A natural transformation, let's call it P, taking F to G, consists of, the picture of this is like you have C, you have D, you have F, and you have G, and there's P.
Safe as an example.
What?
Safe head might be a concrete example, I think, which takes you from list just to maybe A.
Yep, that's a good natural transformation. So you can have in your mind here list mapping to maybe that takes, list is a functor from Hask to Hask, maybe is a functor from Hask to Hask, and this thing is called, this thing takes a list and returns, it's called safe head, I guess. It wouldn't be, it takes a list and returns nothing if the list is empty, and otherwise it returns the head of the list. But what kind of thing is this? Well, it consists of a function, just one thing. A function what? No. For each C in ob_C. So for every data type, like in Hask, a function P sub C taking f of C to g of C. So for any data type you start with, you can get list of that type to maybe of that type using safehead.
Just out of curiosity,
Yep.
I know there's like huge communities with programming language and mathematicians. Do mathematicians say morphism or function?
Morphism.
Okay. Okay.
Am I saying function?
Possible. Right there. Well, I mean, what it has.
Oh, these. Oh, sorry. A morphism. And where did this morphism live? It lives in D, because both these guys are in D. So it takes every object in C and returns a morphism in D. It's like kind of a weird level shift. Such that, okay, right. So for every, this is the part that people find most confusing, I think. For every f taking C1 to C2 in C, there's two things you can do. So I'm going to write it in a commutative square way, and then I'll try to write it formulaically too. You have f of C1, and you have f of C2. And f map gives you a map between them. I haven't said anything about G yet. G has a C1. G knows how to act on C1. It has a type constructor or something for C1 and on C2. And it has its version of fmap. So I guess what I'm saying is safehead is more than just this. It has a property that we didn't write yet. Just because for every type you get a map from list of that type to maybe of that type, there's more that safehead does. And that is that if you had a map from A to B, or from one type to another type in Hask, then you're going to get a map from list A, list C1 to list C2. Something's reflected here, but you're going to get a map from maybe C1 to maybe C2. But you also get safehead, and this will commute. Meaning, if you start with a list of C1s and fmap it to a list of C2s, and then apply safehead, it's the same thing as safeheading the list, and then applying your maybe f. So here's list f, and here's maybe's f. Here's safehead on C1, and here's safehead on C2. And you get the same answer either way. It wouldn't be, that's the naturality condition. That means that you're not going to be led astray when you think about safehead and how it applies to functions. So that's what a natural, oops. Here's PC2 and here's PC1. So this, if you know what a commutative diagram just means that these two paths are the same. Or in other words, f of f, which takes place in D, followed by PC2, which takes place in D, is equal to the morphism G PC1, which takes place in D. They all take place in D. This condition makes sure, just like that ev thing before, I mean, it's not a universal property I'm saying here, but just like, kind of like ev, we talked about how like there might be lots of different ways of doing something. I guess all these lines are those ways. And we want them to, like, we want to give the kind of thing that has a special property that will ensure that it's the good, like safehead is good. That's all it means. It's not randomly chosen.
Why isn't that a universal property?
It's not of the form for all there exists unique. Although actually you can. I think there is a way of, funny enough, I think there may be a way of phrasing this as universal property, but. What?
that it has to be for all?
What does?
Once you've gone up to the category level, because
What has to?
that for all has to be true.
For what?
Because now you're talking about for all objects, like so, or elements underneath the category, right?
I'm not sure what the reference. I'm not sure what you're.
When you're looking at the external, as soon as you go from the external view of a set, for instance, which is what you're doing in CAT, right? Because now you're going from thousands of elements to a single, this is just one set.
Okay.
Doesn't that mean that therefore your logic going forward has to be true for all of your elements? And therefore it's just implied in everything you do going forward?
I don't know. I'm not parsing. So is there something I said that made you ask that question?
Just in terms of whether this was universal. And
Safehead, satisfying this naturality condition. It is. Oh, you're talking about universal property?
mentioned it, so
Yeah, someone mentioned it. I said you could probably do it, but you could probably phrase this that way. But I don't know if you can or not, and it's not too important. It's if they're like in category. Someone I know called it category theory of primordial ooze, because eventually you start seeing that everything can be understood in terms of everything else. Like a category is a monoid in the category of spans or something like that. Like there's all sorts of like, you can take monoids or categories or profunctors or functors. You start with anything you want. You can define everything else in terms of it. So it's all like really neat in some way, and also like if you go to the NLab, for example, you'll start getting into the ooze. You can't start. You have to already know a lot before you can use it. It's like a dictionary where everything's defined in terms of everything else. And so if I can do this, if I can, what did you say?
That's like all dictionaries.
Right. If you can define this in terms of a universal property, that doesn't mean it's the right way to think about it, a nice way to think about it, at least not for an introductory course. Okay, so so this is what a natural transformation is. And so what I want to ask is, let's define graph homomorphisms and then see if they're natural transformations.
A graph homomorphism?
Graph homomorphisms. So let G and H be graphs. A graph homomorphism F taking C1 to G to H is one, a function vertices, like G's vertices to H's vertices. Two, a function from arrows in G to arrows in H. And such that, so you have two graphs, right? You map all the vertices of one to the vertices of the other. Map all the edges of one to the edges of the other, or arrows. But you can't just throw those edges anywhere you want. The source of the edge should end up being at the source of the edge you sent it to. Like, I can't just, if I wanted to send this graph to this graph, I couldn't send this object to this object and this arrow to that arrow. It has to touch the same two things, such that something commutes. So,
Well, the example you just drew, can there be a graph homomorphism between those two graphs?
yes, I could send this one to this one and this one to that one.
But you have a third dot over there.
Yeah. So they're thinking of graph isomorphism.
Oh.
I just need to send dots to dots and arrows to arrows, and they don't have to be onto or surjective, such that I'll just say respecting source and target. So why don't I let you talk to your neighbor, and you can talk about anything that we've talked about so far. But if you want something specific, ask yourself whether, so a graph G is the same thing as a functor from this thing to set, right? So I now have two functors, G and H. So I have G, S and T, and A and V. And I have two functors from that thing to set. I have G and I have H. Is it the case that this F thing with this data is exactly the same as a natural transformation, or is one more general than the other, or are they completely incompatible? So as a exercise, talk to your neighbor about anything you can to get yourself to this question, and ask this question. Okay, give you 5 minutes to do that. Do you guys want clarification on the question? Okay.
I realize what a graph homomorphism is. Let G and H are graphs.
And I told you before that a graph is the same thing as a functor from that thing to set.
With this other
So with that regarding a graph as a functor, I could ask whether natural transformations give you the right notion of graph homomorphism.
I think it is, because basically
And that's your question.
G's a B stage index. So basically, for every because the homomorphism being asked about figure there is basically going to for the arrow.
The one-liner as to what a natural transformation is?
It's a map between functors.
That's what I thought. Functors map between categories.
Natural transformation functors. Say again?
all the four arrows.
All of the 4 arrows?
The union of those arrows in a specific way that allows
So safehead is a map between functors. But the 4 arrows are a sanity check about safehead. Sanity check? Yeah? It's checking that if you have a list and you ask for its head. Yeah?
I just don't get what the natural transformation is like to safehead with the other functions. You do the same
Safehead works on any type, right? You can take list A to maybe A, and from list B to maybe B. Any type, int, string, whatever. Safehead works on all of them. That's number 1 there. For each C, there is a safehead map, P safehead sub C. The second thing is a sanity check. It's a condition that if you have any map in Hask from string to int, you could say length. You could do length and then safehead, or you could do safehead then length, and it gives you the same thing. Say again?
The natural transformation is those two properties.
It's one structure, which is safehead for C, and it's one property. It's like it's one data. It's one constructor, maybe one data constructor. Safehead. What is that? It's no. It's neither. It's a natural transformation. For every
Yeah, because we're moving from lists to maybes. So we swapped out the functor. It was the list functor, now it's the maybe.
yeah, but it's not just that we've changed to which functor we're applying. We have a map from. We have a function in Hask from the list from list of A to maybe of A. Yeah.
I feel like functor changes the A to a B, and natural transformation changes the F to a G, or C to a D.
Yeah, it's not bad. Yeah.
The inner part, one changes the outer part. I don't like inner and outer, but when you draw them on the screen,
Yeah, maybe.
F is outside.
Functors take objects to objects and morphisms to morphisms. Natural transformations take objects to morphisms.
Oh, they lift, or well, but they go up or something.
They go up.
So every time I hear go up, I think Python category. Is there any relation?
Say again? Actually, yeah, return for a monad is a natural transformation. And join for a monad is a natural transformation.
One goes up and one goes down.
Yeah.
The vertices of G to the vertices of H. And another function of action arrows of G to arrows of H.
Say again?
I think yes.
I always do that. I say 1, 2, 3, 4, A, B, C. Like I list all my stuff that. That's the whole thing.
Have an arrow. Then
I don't know. For categories, I said it's 1, a set of objects. 2, a set of morphisms. 3, identity. 4, and 4 composition. Those are the things you need to give me, such that A, this, B, that. For functors, I said 1, 2, A, B. For natural transformations, we're down to just one check, one thing to give, and one check.
The question is whether it's a transformation.
Okay. All right, so answers or questions? Questions? So do you guys have an answer to this question?
I say yes.
Exactly the same thing?
Wait. Oh, I thought the question was whether it's a natural transformation.
Does anyone else have an answer?
You're asking whether G and H are the same thing? Or?
No, I'm asking. A graph homomorphism, I told you what it is. It's a way of taking vertices in G to vertices in H, arrows in G to arrows in H, with the sanity check that, of course, source of arrow goes to source of arrow, and target of arrow goes to target of arrow. I also told you that G could be regarded as a functor from this little graph indexing category to set. And I gave you that kind of translation over there. And H also. So these G and H have gone from being dots and arrows to functors. And I'm asking, if we think of them as functors, we can ask about natural transformations. If we think about them as graphs, we can think about graph homomorphisms. Are we thinking about the same thing? Or are we thinking about two different things? There is a graph homomorphism between G and H, the same as a natural transformation between functor G and functor H. Okay, do you have a question? Okay. So the answer, well, let's see. So first of all, a natural transformation needs to give, for every object in C, a morphism in D from F to G. Okay, so F has become G and G has become H in this thing. Okay, so for every object in C, we're supposed to give a morphism in set. So for V, we're supposed to give a morphism in set from G of V to H of V. And I did give you one. So it's called, I said you're supposed to give me one. And I said you're supposed to give me one from G of A to H of A. And that's the other object in C. Because this C over here has two objects. So I'm just giving two morphisms, two functions. G of A to H of A and G of V to H of V. And then I kind of waved my hands and said respecting source and target. And what that really means is that if you have G of A and you have G of V, you can take the source of any arrow and get an arrow and get a node or vertex in G. Or you could apply your function F, FV, say. Then you could apply your function, or you could do the other thing. You could do H. So you could take your arrow in G, map it to an arrow in H, and look at its source. Or you could take its source and map it over. And that respecting meant that those should be the same. But this is exactly the square we needed for the source function from A to V over here. So the answer is yes. It's exactly the same thing. There's another one where S's are T's. So again, natural transformations are a lot of times where people start to feel like they're in over their head. But then like when you come back in a year, you're like, well, yeah, that's what it would have to be or something. Like you're going to get it at some point. It's just a lot. Yeah?
Is that the definition of a graph homomorphism, or is that what you just told us for this example?
So if you look up graph homomorphism, and when they say graph, they mean directed multigraph, like what we're talking about, that will be the definition of graph homomorphism.
So it's the same thing as saying naturality.
Naturality of functors, yeah. Yep. So, right, yeah. It's also what people call a database homomorphism. If you think about this as a database schema, and you start thinking about these as the data inside. Like this is the schema for graphs, and if I want to give you a graph, I would just fill that database with data. So G and H are two different database instances, and this is what's called a database homomorphism between them. It's a natural transformation. It just means to respect all your foreign keys, basically. So the arrows in here become foreign key columns, and I don't know if I'm helping or not, but the point is that we can regard, right, yeah. So for every two categories, C and D, so given two categories C and D, there is a category fun CD. This category whose objects are the functors from C to D and whose morphisms are the natural transformations between functors.
Just say it again. Just say it one more time.
I'll say it again. For every two categories C and D, including Hask and Hask, there's a category called fun CD. Its objects are the functors and the Hom in fun CD from F to G is a set of natural transformations P. I wrote NT for natural transformation.
I feel like we just keep on being like, okay, we got sets. Now we're going to do sets of sets, and we're going to do functions of functions, and we're going to do functions of sets and sets of
Primordial
functions.
Ooze.
Just keep on adding more and more.
Yeah, exactly. So it's there's a lot of structure that can be. So what that means is functors from Hask to Hask forms a category that you don't have to think about if you don't want to, but you can compose them. You can. There's an identity functor. You get a functor out of this. You get a category out of this.
What's the name of the category?
Fun CD.
Fun CD.
Can I ask you a question? Because like you said that this is where natural transformation of people's brains explode.
I don't know.
But isn't
think.
it kind of like a function is between, within a category between a dot, arrow, dot.
Yep.
And then a functor is basically I take those categories, I collapse them down to dots. So now I've got a dot, which is a category, and an arrow to another dot, which is another category.
Yep.
And then now if I collapse that down to a dot, then
That's a little. That's not a collapsing. That's not a collapsing thing, though. So what actually happens is the second.
Transformation is not a,
Yeah, it's not, so it's actually a next level of. It's maps between functors. So you want to keep your categories around. Note I kept my categories around to talk about what the functors are between.
Because it's really describing different ways of going between
Yeah.
two categories.
Yeah.
Oh.
So C and D. We talked about safe head from list to maybe. There's also one from maybe to list.
But isn't the fun CD, isn't that what I just said, where now you're talking about the functors are, is that what I was talking
Yeah,
about?
I guess maybe. And fun CD is an exponential object in cat. I don't know if that was fun to say or not. Did that hurt or not? I don't know. So,
Why is that?
so you can multiply two categories. You can times them. You can take Hask times Hask. You can do whatever. So you can take C and D, and you can multiply them. What that means is this. I'm going fast here, but I don't know if you'll just follow along. So the objects of this thing, an object in this thing is a pair. Object in C, object in D. A morphism in this thing from C1. So the objects are CD pairs. Given C1 and D1 and C2 and D2, each of those gives me an object here. And a map like that is just a map C1 to C2 and D1 to D2 in their respective categories. And composition and identity, they both come from. This is just a category. So C times D is a new category. And this is a product. It satisfies the universal property for products in cat. We're back to square one or something.
And therefore it's exponential just because.
And exponential means that C, so Hom in cat, from C times D to E is isomorphic to Hom in cat from what to what?
C to E to the D.
Yeah, C to fun DE, or you could write that as E to the D.
That's not, isn't that level where you're talking about, now you're talking about it's categories and morphisms, and then you're, like,
I don't know if this is helpful for anyone, but it's true. Yeah. So why don't you? Is it no, okay. So how about this? How about another thing to work out? Wait, what do we end in 25 minutes? What? At 3, right?
And you're still going to talk about that.
Oh, we end session 2 in 25 minutes, and then then session 3 starts half an hour later. Say again?
Who's going to get the adjoints still?
Yeah. So, yeah, the plan was to get the adjoints right now. So,
One quick, is there one little add for horizontal for monad transformers? Where is that? You don't when you layer on monads
oh,
or functors or however you want to call it.
yeah. I mean, are you talking about distributive laws or monad transform? I don't know.
Yeah, when you so horizontal is vertical, right?
No, I don't know about that. I use that in a weird way. I mean, I don't know about that doesn't mean I don't know about that. It means I don't know about. Any other questions? Okay, so yeah, so if you are interested in this kind of databasey approach where you have categories and you have fun C set, in fact, these guys form what's called a topos. This is a category. It's got lots and lots of structure. It's a higher order logic structure, makes sense for a fun C set. It's a topos means you have times and plus and you have exponential objects and all sorts of stuff. And this, but you can also look at fun C set as all databases of shape C. C is going to be some category with some objects and some morphisms, whatever. And fun C set you can look at as databases of that schema. And so if you're interested in that kind of thing, we have a software tool called FQL, which is not Facebook query language, but functorial query language that's open source. And it kind of is a place to play with these ideas. Like there's all sorts of joins, like database joins and unions and all sorts of different structures make sense in terms of category theory. Like they have category theoretic analogs, which this tool, this open source tool, can tell you, can give you a place to play with those ideas. So, and someone, my colleague, is talking about algebraic databases at last session of tomorrow. So he'll talk more about this if you're interested. So it's kind of more category theory, but in like a database context. So I think in the next session I'll talk about adjunctions and about monads and stuff, and I'll skip the last stuff. So
What's the last stuff that you're going to
it was about monoidal categories. But I have to go the pace of the room, I think. So, so do you guys want to work out what fun star C is? So star, what's star? Star is the category on one. You take this thing and you look at that as the unique object and just the identity morphism, which I don't even usually draw because it's always there. And that's, I'm calling that star. It's a category. And so it's sometimes helpful to think, okay, in math it's always useful to like work on the smallest example that you don't yet know, even if you think it should be obvious. So this is a category. What category is it?
It's a C, right? Category from your...
It's a functor category from star to C. So what would you need? What is the data of this? It takes a functor from star to C. So what are the objects of this category? The objects of this category are the functors from star to C. What is a functor from star to C? So we're going to like pop in, like you have like these plus signs, we're going to open up them one at a time. So first, what is a functor? What are the objects of this category? That's thing one, opened. Then we'll talk about the morphisms. So the objects are functors from star to C. What's a functor? It's something that takes objects of this to objects of this. Okay, let's open that up. The objects of this, there's one. So we're supposed to give one object in C. So a functor just takes this unique object and gives one in C. and takes the identity morphism and has to send it to the identity. So there's no choice on a functor from star to C except where it sends the object. So a functor,
Number of functors is the size of C.
the number of functors from star to C is the size of the objects of C, the number of objects in C. So what we found is that the set of objects in this thing is a set of objects in C. Yeah. I mean, a functor is a lot of data, but if you break it down, they're in one-to-one correspondence with objects in C. What's a morphism in fun star C? It's a natural transformation from this guy, right? So it takes, what is that? Oh, I erased it. It says for every object in here, I need a morphism in here. So I'm now in morphisms. Hom from F to G. So F and G are functors from here to here, but they're just objects in C. So maybe I'll just call them by their object name, like C1 and C2. C1 is the name of an object in C, but it's also the place that my functor took star. So Hom from C1 to C, actually I'll call it like FC1 and FC2. So what's Hom in the functor category from FC1 to FC2? It's a natural transformation, which means for every object here, I need a morphism here. And for every morphism here, I need to give a square commuting. So for the unique object there, I've sent it to C1 and to C2 in my two different maps. And this is going to be a map between them in C. And if you work it out, it's isomorphic to Hom in C from C1 to C2. So whoever said that this was exactly C, they were right. Hom star C is C. Fun star C is C.
The star is like a left identity.
Well, this kind of says C to the star is C. So star is like 1.
Is this like the indexing?
C to the 1 is C.
Is this like an index?
1 is this guy. Indexing? What do you mean indexing?
Like that thing indexes C.
It indexes objects. Yeah. Maybe you'd say it indexed the identity functor on cat, or I don't know. It represents the identity functor on cat or something. So actually that's right. So if someone knew what represents means, then they would understand the statement that star represents the identity functor on cat. But I don't know if that's helpful to anyone. Probably not. Right, so what we have, we have the arithmetic we had for sets. We also have for categories. We have coproducts and products. We have associative law. We have like C to the D times E, C to the D to the E. I don't know. These are all functors. I think I'm just like tired or something. All sorts of stuff that we said about arithmetic for sets, like A plus 0 equals A, and A plus B, we didn't say this, but A plus B times C, like if you take two sets, you coproduct them and you multiply by a third set. That's isomorphic to A times C plus B times C. All sorts of arithmetic rules work for sets just like they do for numbers. And they also work for categories just like they do for numbers. So like there's this fun CD thing, but that you could write, as someone even said, in exponential notation. And that exponential notation will work correctly with respect to all the usual laws of like plus and times and stuff like that. Like C to the 0 will be 1. And C to the 1 will be C. And stuff like that. 1 to the C will be 1. 1 is that category with one object and just the identity arrow. And this says that functors from C to that category, how many are there? There's exactly 1. There's one functor from anything to this. It sends every object to this one and sends every morphism to the identity.
Is that like the terminal?
So that's what that says.
That's the terminal.
That's the terminal category.
Terminal category.
Yep, that's a terminal object in the category of categories.
What does the 0 represent?
0 represents the empty category with no objects and no morphisms.
So there's one.
There's one functor from empty category to C.
What was 0?
0 is the empty category. Yep. No objects, no arrows, morphisms. The disjoint union, the plus of two categories, you take all the objects of C, all the objects of D, and you just union them all together. You take all the morphisms of C, you put them all in there, all the morphisms of D, put them all in there, and nothing connecting D's and C's. Just two categories side by side living as one big category. That's plus. Yeah?
And we know all this is true because we have a functor between, like, say, the set of numbers and categories.
No. Why do we know that these things are true? It takes a proof. Yeah. Yeah. It takes a village. Do you have a question? That's his joke. Yeah, no question. Okay. So I was going to talk about adjunctions next, and I guess I'll start. Okay. All right. So we're going for 14 more minutes, and natural transformations were tricky. Will adjunctions make sense? Well, so do you want more examples of natural transformations? So we had SafeHead, but was there any other ones you want to see?
The second element of the list.
SafeTail. You can go from maybe A to even list A. Right, so how would you go from maybe A to list A? Oh, sorry, maybe to list. Maybe A to list A, there might be tons of ways. I'll take my maybe and I'll send it to the list with I'll send to the empty list or something. But maybe to list, this is a functor from Hask to Hask, and this is a functor from Hask to Hask, or set to set. And this is saying that for every type, if you look at maybe of that type and list of that type, you can map between them without even knowing what that type is in advance. And that's what functors are about, natural transformations are about. You have two different functors, and you can map between them every time. So what is it? Where do you send?
Because then the list, the empty list is the not there, and otherwise it's a list of one object, which is.
I'll go to singleton. If I just have an element of this, I'll give it to a singleton, and if I have nothing, I'll go to the empty list. That's a natural transformation. It'll work right with every. What does it mean? It's natural. It means if I have a map from A to B, I get a map from maybe A to maybe B. So let's review natural transformations again. So maybe A to maybe B. It takes just anything in A and gives you just that thing in B and takes nothing to nothing. And I have list A, and I have list B, and I have list F where I map F over my list, no matter what A and B are. But I also have this thing that goes kind of like empty list or A. I mean, is that right? Does anyone have a nice name for this map? Do you guys see it or no? Yeah, okay, great. Maybe to list. MTL. MTLA and MTLB. Maybe to list, yeah. And if you take your maybe A and you get your maybe B out of it, whether it's nothing or whether it's just something, and then you get a list, you'll get the same list as if you first listify it and then map. And that sanity check is the naturality condition. Mathematicians, I think, had been saying that something was natural, but the McLean and Eilenberg gave a definition, which is that this thing commutes for all arrows in Hask or whatever, all arrows in C.
So, I mean, for any function from like one type constructor to another that's mapped, we have naturality in Hask because of parametricity. But that doesn't mean that in other categories, like, you can still have, can you have a morphism between functors and other categories?
Wait, you're trying to say that you think for any two functors, there is like...
If you have parametric...
Electricity might be the naturality condition.
I think what he's saying is that if you have a function of type like for all a, f of a is g of a, that's necessarily a natural transformation.
Is that right? It always has this property?
I think so.
Well, I mean, you can't guarantee that, right? Because in any, like in programming languages, you never actually guarantee the properties. Like the programmer is like saying, like, I promise this really is a monad, even though all you've really given is the constructors, right? Like you don't check.
Yeah, I think
There's no, like there's often, it's undecidable to check whether this commutes for every possible function.
Assuming non-termination.
Huh. Okay, it might be.
But you're not saying that that's...
I'm worried that it's going to be the same as the ev problem. Like you think there's only one ev, but really there's evs that aren't the real ev. You don't think so? Okay. I'll take your word for it. But
my question is, that's not true of other categories? Like,
yeah, so like, what's a natural transformation?
that makes me worry that it's not true. But what?
Parametricity isn't necessarily... Yeah, it has to be types.
Yes. Right.
So what if I had a functor from set to set? I can't believe I'm about to try this. So I'm going to give a map here. And what I'm going to do for P is I'm going to send every function between... No, I can't do it off my head. Adjoints, yeah. So I really doubt it. I doubt that it's automatic, but that just means we have more to talk about. Okay. Okay, so I have 9 minutes left, 8 minutes left. So I'm going to say adjoints. So adjoints, adjunctions. Okay, these are the same idea. They're the same thing. So an adjoint starts with two categories and two functors, but now they go in different ways. Actually, I'll call L and R functors. So I don't know what lenses are, but I think that there's a way of viewing lenses in this setup as adjoints, or adjoints might be particularly nice lenses, but don't hold me to that, and don't take my word for it at all. So these two things are translators between C and D, and they are not necessarily an isomorphism of categories or equivalence or any kind of equalness. This could be the terminal category with one object, and this could be just set, and this might be the functor that goes to the empty set, and this might be the functor that is the unique functor of the terminal category. Like they could be very different sizes. This one could have one object, this one could have as many objects as there are sets. But I have a way to go forward and a way to go back. Then we say L is left adjoint, or that R is right adjoint to L. So L is left adjoint to R, or R is right adjoint to R, L, right? Adjoint of the left adjoint of L if, all right, let's break. Okay. No, okay, I have 5 more minutes. So if there is a natural isomorphism.
Are we talking about C and D or L and R?
So the things that are adjoint are L and R. And those are functors from C to D and D to C.
Do you have examples of just like
I'm going to get, yeah.
human life, like babies and cars, or cats and dogs, and buildings and...
Yeah. You could have babies and adults. And you have baby language and adult language. And every baby language, I'll just try to translate it into adult language. I'll translate it just as what I think they're trying to say. And for everything in adult language, I'll just take it as sounds. And maybe that works. I don't know. I wrote it in my book. I wrote that exact example, but I actually wrote it out. And I think it almost made sense. But I don't know, yeah. So let's see, if there's natural isomorphism. Okay, so this looks really complicated. Maybe I should have started with the example. But L of C to D is isomorphic to Hom from C to R of D. So if for all CD, C in ob C and D in ob D, there's an isomorphism. That thing to that thing. And that's actually a natural isomorphism, which means you have, well, I'm not going to say. It's natural with respect to changing in C and changing in D. And I could go into that if you want, but maybe I'll wait. I think what I should do first is give you the example, and then we'll take the break, and then. So in set, fix a set A, or a Haskell. This really works best in Haskell, or I mean, this is fine. You could think of Haskell. We're going to do currying as an adjunction. Currying as an adjunction. Currying and timesing. So let L, so we have set to set, L and R. Let L of X be A times X. That's a functor from set to set. It takes every set, returns a set. It takes int, returns A times int. It takes a map from string to int and returns a map from A times string to A times int by doing identity on the A side and the map on the other side.
Fix a set?
Oh, let's just talk about one set for a moment. A.
So then, can we just call it A in the diagram, or is it not A in the diagram?
Let's call it L sub A and R sub A. Is that better?
And the set's on the left, that's an A, and on the
Yeah, that's what I mean.
I'm kind of doing some currying even. So I'm going to give you an adjunction for every set A. But I'm just fixing one, so you just have one adjunction instead of like a whole set indexed bunch of adjunctions. So is that okay?
Yeah, I got it. Thank you.
This is a functor. Why? Because it takes any type and returns A times that type, and it has a map. Because if I had a map X to Y, I'd get a map A times X to A times Y.
what's the A in the what's the X in this?
It's the functor, so for any. No, sorry. X in ob set. So take any set, return a set. I need to give you a functor from set to set, and I told you on objects, I'll take any set X and return A times X.
What's it mean to be A times X? Oh, the functor times the
Products.
Product type.
The functor with the product of the functor and the set.
No, the X is a set, A is a set. I can therefore multiply them and get a new set.
Oh, okay.
Just like we were doing in the first hour.
In the first hour, yep. Does anyone have a guess for R sub A of X?
What's on?
R is going to be this guy.
Oh.
It is, or let's call it Y. So for any X sets X and Y, RA of Y is going to be the arrow type, A arrow Y.
Oh, that's like you apply it? It's like the result. One of them goes together and basically you execute your valid.
We're going to have a break, and we're going to come back, and we'll start again on this. Okay, so see you in half an hour.